Okay, circular motion. Two types of circular motion. Firstly, horizontal circles. So whenever you've got a particle travelling in a horizontal circle, you've always got two different things happening in the two different directions. Firstly, vertically, the particle is in equilibrium. So you can use F equals ma and have acceleration equals to 0, but I think it's much more straightforward. If you've got equilibrium, if you just say forces one way, so forces up equals forces down. The more interesting part is what's going on horizontally. The particle is accelerating towards the centre of the circle. Of course, that is because even though the speed is constant, because it's always changing direction, that means that the velocity is changing. The velocity is changing, so there's got to be an acceleration, and that is towards the centre. Because you've got an acceleration, you're going to be using F equals ma, which of course is consistent with what we've done in ordinary maths. F equals ma, remembering that that F means resultant force in the direction of motion. So you are going to be resolving your forces acting towards the centre of the circle. The A, of course, is equal to omega squared r, where omega is the angular speed, or v squared over r. So we are going to look at this question. This question, an exam question taken from the old spec. It's a decent standard, 11 marks. If you look at the question number, question 6, and generally there were 8 or 9 questions on a paper, so it's getting towards the tricky end there. Of course, it's starting off simple, however. So the situation is we've got this horizontal plane, and there are two particles threaded through a hole in the card or the whatever it is. A light inextensible string, length 1 metre, smooth, hole A, and the plane itself is smooth as well, so there's no friction. One end of the string is attached to a particle P, that's 0.5 kilograms, and it hangs in equilibrium. That, of course, is key. Because it's in equilibrium, it means that forces are balanced on P. The other end of the string is attached to a particle Q, and we know that mass, and that is the one that is, of course, rotating with a constant angular speed, and the radius of that circle is 0.2. What we need to work out, find the tension in the string and then the angular speed of Q. So P is where we need to start. Because P is in equilibrium, it means, of course, that forces are balanced there, and we can easily work out what the tension is. Because the tension in the two parts of the string is the same, it's the same string, there's no friction happening there, so it's going to be the same tension. So we start by looking at what's going on P. And look, I'm writing down what's going on with P. Some of you, you need to make sure you're writing down what's going on every time. So on P, I am looking at what's going on in the vertical direction. I know it's in equilibrium, so I can say that the forces up, which are tension, are just equal to the forces down, which is mg or 0.5g. So I can just say forces up equals forces down. So T is simply equal to 0.5g. That's it. That's all that's going on with P. There's nothing going on in the other direction. It's not moving. So now I can move and look at Q. We could look and see what's going on with Q vertically, but there's no need. We'd have the normal reaction and the weight, they are equal, but that's kind of irrelevant. What we need to look is what's going on in the other direction. So here is Q. I've only got one force acting towards the centre of the circle, and that, of course, is T. That is the direction that we then would consider that acceleration. So if I'm using F equals ma, I'm, of course, looking at what's going on in the horizontal direction. Using F equals ma, only one force, T, is equal to m. And, of course, I've got two choices for A. Because it's wanting angular speed, I am going to use omega squared r. I know what T is. T is the 0.5g. I know the mass. The mass is 0.3. Omega is what we need to find, and r, of course, we've got to be meters, is equal to 0.2. Working through that then, we get that omega squared is equal to 0.5g dividing by the 0.3 and the 0.2. That gets me 81 and 2/3, so I know that omega is the square root of that, which works out to be 904, and the units for that radians per second. Okay, so that should be standard. There shouldn't be any issues there. However, it gets a little bit more interesting in the next part of the question. So we now have Q being fixed. So Q is there, that isn't moving. So, essentially that is irrelevant. P is this time the one going round in a circle. That distance there, of course, is important now because it means that we know what this distance is. That distance is equal to 0.8 metres, and that is going to help us to work out that radius of the circle. And it's always worth doing this, I think, as a little separate calculation. So I might just do that here. I have got 0.8 being the hypotenuse. I know that this is equal to 0.2, and I've got a right angle there. It tells me it's 0.2. That's how I knew that that was 0.2. I need to work out this length. Oh, we could use decimals, but I'm sorry, I'm just going to go with lovely fractions. 16 minus 1 gets me 15, so I know that's root 15 over 5. So I hope that what you're doing every time is that you are writing down exact values here. I can work out that angle, but I know that if I needed to work out sine, I could just use that 15 over 5 divided by 4/5. So we would have, for example, that sine theta is equal to the opposite, root 15 over 5 divided by the hypotenuse, which is 4/5. Of course, the fifths cancel, and I'm just left with root 15 over 4. So it means that you don't have to faff around with decimals when you don't need to. Okay, let's actually kind of check out what's going on with the question then. Calculate the tension in the string. Now here, I think it's crucial to draw a separate diagram to see what's going on. Of course, we're looking at P. P, we've got the weight acting downwards, that is equal to 0.5g. The tension is in that angle there, but my acceleration, the direction of the acceleration is acting directly towards the centre there. So I'm following the convention and having my accelerations as double arrows, my forces just as a single arrow. So I can easily see what's a force and what isn't. This angle that I referred to up here is there. Now, two different directions. Look at what's happening vertically, because vertically I know that it is in equilibrium. Because it's in equilibrium, I know that forces up equal forces down. So that component there is the component going up. So some of you, might like to draw out a separate triangle. If I just kind of mark that out there in a different colour, I can see that that's going to be the sine component. So I know that the force going up is T sine theta, and of course I've got my expression for sine, which we can pop in there. There's no other forces going up. The force going down, that's equal to 0.5g, and that's all going directly vertically down, so I don't need any components there. I know what sine theta is. So I've got 0.5g over sine theta, and sine theta is equal to root 15 over 4. And if I work that out, I get 5.06 newtons. And then to calculate the speed of P, there of course we are looking at what's going on in the horizontal direction. In the horizontal direction, of course, it's not in equilibrium. We're going to be using F equals ma, where F is the resultant force in the direction of motion. There is only one force acting horizontally on P, and that, of course, is the other component of the T. So it's almost automatic, because you know that T sine 30 was the vertical component. The other component, the cosine, is going to be the horizontal component. So I've got T cos theta. That's the only force, and that's equal to ma. So equals mass times the acceleration, m. It's wanting speed. So if we go with v squared over r, and we do know r, don't we? That is, that's the 0.2, and yeah, told it there. So T, I know T, 5.06. I know cos theta. So if we look back at this triangle here, cos opposite 1/5 divided by the hypotenuse. So cos theta is 1/5 over 4/5. So that's equal to 1/4. So 5.06 the tension times by 1/4, which is cos theta, and that's equal to the mass, which is 0.5, multiplied by v squared divided by 0.2. So I've got an equation with v squared in. So 5.06 times by 1/4. I also want to times by that 0.2 and divide by the 0.5. That gets me 0.506. So v is equal to the square root of 0.506, 0.71. And that is the speed. So that's meters per second.